for you to do the multiple linear regression in Excel for your assignment. Okay, first of all, when we consider back several weeks ago, we talked about t-tests. Okay, t-tests are just the basic level of um, like a between groups design that um, you then can step up to a one-way ANOVA and then factorial ANOVA. Okay, for correlation, that is the basic level for the relationships variables that you would step up then to a linear regression, which you could use two variables in a linear regression. Then this is multiple linear regression where you'd have three continuous variables. Okay, so kind of the same step up process. So the basic level would be correlation. That's why we're using this data set with the regression assignment as well. You've already looked at it to check for normality and things like that. There is something in regression that you have to consider, and that is called multicollinearity. That's a very large term, but basically, if you cut it down to just the basics here, multicollinearity is just saying that we do not want the predictor variables to be too strongly related, because you doing so, you're not going to be able to figure out the which one of them are actually related to the or actually predicting the outcome variable, and it just makes it much of a messier data set if you have um, too much correlation between any of the predictors. Okay, so that's called multicollinearity. Now, if you go back to your assignment um, for correlation, these two variables did not have a very strong correlation. Okay, I think it was 0.15 or 0.16. So that's not enough to be concerned about. The correlation should be pretty strong for it to be problematic. And there's ways to check that too. But again, this is your first time dealing with regression. So I want you to understand, though, that there are more pieces to this, and it takes a lot more statistical knowledge to um, make sure that everything is done the way it's supposed to be done. But I just want to get you guys the basic understanding of what a regression is. Okay, so we have pretest and study time. These are our predictor variables, or if you want to think about independent and dependent variables, these are the independent variables, okay? And then post-test, that's your dependent variable, which is called a criterion variable. So that's the outcome variable. So we're trying to predict post-test based on pretest score and study time. So when you look at a regression, so a simple linear regression, the equation for that is y equals bx plus a, okay? So y would be, like this would be y, this column. These are the y's. And you're trying to predict, so this equation part is you use these variables, right? So the x's are each of these specific numbers. So once we run a regression, then we can create our prediction equation. And then we could plug numbers in to pop out what the predicted post-test value is. So we're trying to figure out what equation best fits this model, okay? And is this model a good fit in general? And I will explain that to you once we run the regression. But if you have been in math classes, you know that y equals mx plus b. That's very similar to this, right? So b is the slope, and A is the intercept. So think about unstandardized betas, which is what will pop up in your regression. Unstandardized beta 1 and 2, because you have two independent variables, so they're depending on how many predictors you have, that is going to show up in how many of the betas you have. And then the A, that is the y-intercept. So that's a baseline. So that's a static value that is added to um, get to this predicted value. Okay, so first of all, since this is the same data set, I'm not going to select all the data. You guys still have the 50, the observation size of 50, but I will be using just a portion of that, so it's um, not giving you all that extra information. So you have to get it done for your assignment, okay? So you just need to follow the same steps and you'll get to the correct answers. Okay, so when you look under the data tab where there's data analysis, you go to regression and then click OK. Now in um, in this in this sample, I'm going to use 35. So I am using C1 to C36 as my Y range. So I said these are the Y's, this is the criterion. And then for the X, I have to have, these have to be next to each other because I'm including both of them. And I selected A1 to B36, right? So, and since I selected the first row, I'm going to click that there are labels because that's will pop up here. That this is going to be um, labeling the variables in the output. So as far as the output goes, I'm going to put that starting here, and then I'm not going to click any of this extra stuff, but I'm going to click OK. Okay. So it pops out this information, and there's there's a lot here. There's not as much as for what we have for the ANOVA because of all the things that I had you look for, but there's still a lot here, and you got to consider what each of these things mean. So we have our coefficients. So these are unstandardized beta coefficients. So I'm going to highlight that because that's really important. And our p-values, we always look at the p-values. We know that's important. And then we have an ANOVA, which that's kind of funny, right? Because I asked for a regression. So it's important um, to understand what this is actually telling you. This ANOVA is telling me, is my model statistically significant? Is it a good fit? And if this is statistically significant, that would indicate that my model is a good fit. But we can see I didn't select all the data, right? So this is going to be different than what you have, but it is not. My model is not a good fit because this is not statistically significant. Okay? So it's not a good fit. But I'm going to keep like looking at things just kind of to show you, because normally what you'd want to do is, okay, I need a different model. Like I'm missing something. I've got to look up at what's going on, right? And one of the first things I would probably do is increase sample size, which is what you guys basically will be doing because you're using all the data. So I'm going to go ahead and look at these coefficients and the p-values. So the intercept, if you remember up here, the intercept is the a value. So let's go ahead and start writing in. So y is then bx1, or b1x, sorry. It doesn't matter how you write it, just knowing what it is the important part. b2x, and then a. So in this case, a is the intercept. So we have to look at what coefficient, and this is statistically significant, right, at the 0.001 level, and it's going to automatically pop that 0 in front of the decimal point, even though APA style doesn't use that. But okay, so if you move the decimal point over 5 places to the left, because see it says 05 over here, that means you need to move it 5 places. It's definitely statistically significant, and it's actually below this level, but that's why when I write it out, I'm going to say p is less than 0.001. But that's the typical. You have 0.05, 0.01, and 0.001 is the standard way of writing these. So 56.056. So I'm going to have to round that, right? Because I want 2 decimal places. That's typically what I ask for. So 56.06 would be A. And then now I'm going to just put the B2, and then I'll explain to you how to use the X and the B1. Okay, so B1, that would be pretest. So I'm going to put that up here just to kind of explain this a little better. Study time. This is predicted post-test score, and then this is just a constant. Okay, and that's p-value. That's just kind of to note it's not part of the equation. Okay, just showing you that note. But I'm going to move this so it doesn't get confused. Okay. So our unstandardized beta coefficient for pretest, that is 0.34 after rounding. And then for study time is 0.84 after rounding. So here is our equation. So you have y equals 0.34 x1 plus 0.84 x2 plus 56.06. Okay. So, and because this model is not statistically significant, I'll explain what these are up here, but basically this model isn't as predictive as it could be. It's not a very good model, but I'm going to explain to you what these parts are and how to use them. Okay, so if I were using this equation and I wanted to plug numbers in, so I don't add a y because that's what I'm trying to predict, right? Pretest is this number. Okay, so let's say somebody got a, let's say somebody got a 56 on the pretest. So I would multiply, so 0.34 times 56. And then that gives me a number. And then I'm going to do the same thing on that same row. Right now I'm focused on this row, right? Okay. So if I take 0.84 and multiply that by 13, because x1 is going to be whatever variable you have here, x2, whatever variable you have here, and then so it corresponds with the correct study time is going to be multiplied by what their actual study time was. So pre-test, this is going to be multiplied by what their actual pre-test score was. Okay, so then that gives you 1904 plus 10.92, and then you still have this constant, so that did not change. And then, so y equals these things, right? So then y is equal to the sum of these three numbers, 86.02. So it actually didn't do a too bad of a job of predicting that score, but you could see it's not exact. It's not very precise, so it didn't predict that well, right? So that's kind of like how the equation works. For you guys, I'll ask you for the unstandardized beta coefficient for pretest or study time and so on, and if they're statistically significant and so on. These are the confidence intervals. You've probably read about that in your text. That means that we have 95% confidence that the actual coefficient falls between these two numbers. Okay, so that's a pretty wide range here. And the better you get, the smaller this range is. Usually that's going to be with much larger sample and such, but overall, this model is not statistically significant, so I wouldn't use it for any kind of predictive value. But the focus, though, I'm going to highlight that so you guys know that's important. The focus, though, when you're looking at a linear regression, you're often going to see R squared. If you look at multiple regression, it should be adjusted R squared. So these two items are very important. Okay, so now for multiple regression, it's this one. And for linear, so multiple is more than just the two variables, more than just the predictor and the outcome variable. And linear is going to just be the two, right? So if this were a linear regression that I did, you'd have this number that you would use, but in this case, we want to adjust for the number of variables we have. So after all is said and done, this is our adjusted R squared. So what this is telling you, so if we make that a percentage, so I'm going to bring that over here, and I'm going to make that a percent and 2 decimal places, right? So it's 8.19%. So the R squared can tell you the percent of variance accounted for from or in the outcome variable by the predictors. So we can say that 8.9 or 19% of the variance in post-test score is accounted for by this set of predictors. However, the model is not statistically significant. Okay, so this is essentially your effect size. Okay, so effect size. Whereas um, these are your unstandardized betas. That means they can't be compared between each other. Now, if you have a statistical software, there usually pops out a standardized beta coefficient, which would you'll often see within um, within research articles. So these are unstandardized, can be used to write the equation, write your regression equation, but they can't be compared. So I can't say the study time um, is, if these were all statistically significant, could not say the study time made a larger impact on post-test compared to pre-test because these are not comparable numbers. Okay, these are just um, specifically the unstandardized betas. Okay, when you standardize something, like you learned with z-scores a while back, you can compare those numbers. So if there were standardized beta coefficients, it could tell you which predictors made the largest impact on that prediction. But again, this is in um, this is in Excel. It doesn't pop that information out for you, and I'm not going to have you guys do that. So, but it is important to understand that because you'll often read that in journal articles where it will have the beta, which is a beta sign. It just looks like a big B, but a little bit uh, kind of like a cursive B. It'll have the size of those betas, the beta weights, a lot of times called beta weights, and those can be compared together as long as they're not the unstandardized versions. Okay, so I hope this helps. I hope it makes sense. For you guys, I don't have any specific uh, figures that I want you to do this week. It's just running the regression and kind of looking at this information and picking out the pieces, the important parts. And I'm hoping that this can help you understand a little bit more of what those regressions that you read in journal articles are explaining to you. So I hope this helps, and hopefully this audio recorded this time. Um, I I'm glad this is your last video, I'm sure. So I hope you guys have a wonderful rest of the school year.